Projectile motion. By the end of this lesson, we'll be able to describe the motion of an object moving in 2 dimensions. To do that, we need to know that motion in 2 dimensions can be analyzed using one-dimensional kinematic relationships if the motion is separated into its components. Projectile motion is a special case of 2-dimensional motion that has zero acceleration in one dimension and constant non-zero acceleration in the second dimension. Projectile just means it's an object that is moving through the air. Air resistance is the force of the air molecules pushing against a projectile. If there's not enough air resistance to measurably affect the motion, it is ignored or neglected. Negligible is a word I will use. It means a very small amount. Horizontal motion means motion along the x-axis, while vertical is motion along the y-axis. Trajectory is the path that an object follows through the air. Projectile motion is the study of an object's behavior as it traverses along a trajectory. There is a vertical acceleration due to gravitational field and no acceleration in the horizontal direction unless otherwise stated. Range is a term we use to speak about horizontal displacement. Impact velocity is the combined velocity when an object strikes the ground. Rules for projectiles. First of all, if air resistance is negligible, that means there's no acceleration in the x direction. The horizontal component will remain the same magnitude throughout the entire flight. The vertical component, meanwhile, will get smaller until it stops, then speeds up in the opposite direction because of gravity. At the maximum height, there's no vertical velocity, only horizontal velocity and vertical acceleration. Acceleration is constant throughout the path in the downward direction because of gravity. The trajectory is a parabolic shape with a velocity that is tangent to the trajectory. If air resistance does exist, then the trajectory will be lower and shorter because the projectile is being slowed down, which means the x component of the velocity is getting smaller. For the first type of projectile motion problem, this is a horizontally launched projectile, where an object starts some height above the ground and it is launched horizontally with some initial velocity. Remember, we have to treat x and y components completely separate. Here, the launch angle is 0, so all of the initial velocity is along the x-axis. Think about the vector unit. If we're looking at the y velocity, we would do the initial velocity times sine of the angle. Sine of 0 is 0, so there's no initial velocity in the y direction. Acceleration, meanwhile, is still negative 10 meters per second squared. Air resistance is negligible unless it is mentioned. Take a look at these vectors. So we start off this simulation with 0 vertical velocity, and then as it goes through the path, through the trajectory, we see the vertical velocity vector is growing because acceleration is in the same direction as the velocity. It's being accelerated down due to gravity. That's what causes this bend in the path. Same thing happens as we decrease the speed. It's just not going to go as far out. For the next type of problem, we have a projectile that's launched at an angle. Remember, x and y must be treated separately. The initial velocity in the x is the magnitude of the initial velocity times cosine of the angle. The initial velocity in the y is the initial velocity times sine of the angle. That's a typo. The path is parabolic, so there is symmetry we can use. The initial velocity equals 0 meters per second at the top. There's our nice parabola. At the very top of those parabolas, remember our initial velocity, or the final velocity, however you're looking at it, will be 0 meters per second at the top. Take a look at the vectors as we change our angles, our launch angles and speeds in the video. And remember that if you find the time to the maximum height, look at the time in the top of this video, that time to the maximum height is only half of the time, so don't forget to double it if we're looking for the entire time, or if we need the entire time. Of course, we can use our kinematic equations in the x and y direction as long as we're keeping them completely separate. Here I've added in the blue acceleration vector to show you that even if the object is stopped at the top of its trajectory, there's still an acceleration downwards. That acceleration is not changing the entire path, because you can't turn off gravity just because an object is at the top of its trajectory. If you are at a height, it's going to be very similar to being launched at an angle. Of course, we're going to keep x and y treated separate. Initial velocity in the x is initial velocity times cosine theta. Initial velocity in the y is initial velocity sine theta. Sine theta, yeah, don't look at it. The path is only partially parabolic, as we'll see here. So there is some symmetry we can use. If we only want to find the height or the time it takes to return to the same height, then we're looking at just the parabola. But if we find the time to the maximum height, remember with this type of problem, this is not half the time. We're just using kinematic equations for these. And acceleration will still be negative 10 meters per second squared the entire time. Next steps, do some practice. There's not a whole bunch of new information with this lesson. If you do want more practice, use the AI prompt. Provide me with 3 practice problems for conceptual projectile motion problems. Show me the answer, no solution. Change that number from 3 to 10 to 20. Do lots of problems. Ask each other, ask me, and keep asking until you get it.